In Part 3 of Lecture 5, we will discuss the lifetime of a variable. Most data items in a program have a relatively limited lifetime within that program. Older languages, such as Fortran, use static allocation of memory. This means that memory is allocated for a variable at compile time, and it is there from the moment that the program is loaded until it is terminated. It turns out that this is pretty wasteful. A program will rarely use more than a fraction of its data items at any given time. So the computer can make more effective use of its memory by first allocating storage for data items when you enter the procedure in which they are used, and freeing that storage when you finally leave the procedure. This is how dynamic allocation works. Allocation refers to assigning a data item to a particular location in memory. Deallocation refers to making that memory location available for reuse. And a variable's lifetime refers to the time in which that data item is bound to a particular location in memory. While Fortran originally set aside storage for all its variables at compile time, this is rarely done anymore. Even languages that make use of static allocation do it more selectively, with some variables being allocated statically and most being allocated dynamically. As we stated before, static allocation means that dynamic items are bound to the memory locations at compile time, while dynamic allocation means that these data items are bound to a particular memory location sometime during the program's execution. One example of static allocation in more modern languages is C and C++. External variables that are outside any one function are all statically allocated, as are internal variables that are declared using the reserved word static before their data type. The advantage of static allocation is that you can use direct addressing, which does not use the contents of a register as part of the address. This leads to faster instruction execution. However, this comes at a price. It prevents the language from supporting recursion. Stack dynamic variables have their storage allocated when their definition statements are elaborated, which means that the storage is allocated when the computer is ready to execute the code of which the definition is a part. While this is most commonly done when transferring control to another procedure, it doesn't have to be that way. Many languages, C and Java included, allow variable definitions to appear within any block of code. Since procedures are usually handled in a first-in, last-out manner, using a stack to allocate and deallocate memory makes an enormous amount of sense. Scalar variables will have all their attributes, other than address, statically bound. Stack dynamic variables have a few decided advantages. It makes the use of memory much more efficient, and it also allows the use of recursive procedures. But there are also a few disadvantages. The constant allocation and deallocation of memory takes a certain amount of time and slows the execution of a program. Since subprograms do not continually use the same areas of memory, it cannot keep track of any sense of history for that procedure. And it requires that we use indirect addressing, which is much less efficient. Explicit heap dynamic memory variables have no name. They have to be referenced using pointer or reference variables. A heap is far less organized than a stack. This is because its use cannot be predicted as easily as the use of a stack can be. In the case of a stack, we know that we will deallocate the most recently allocated parts of memory before we leave the procedure to which they belong, and go back to the procedure from which we came. In this way, we are guaranteed that we will reserve and free up memory in a particular order, and it is fairly easy to keep track of which memory on the stack is in use and which isn't. But this is not true for the heap. Any memory location that is part of the heap can be deallocated and returned for reuse. This makes it much more difficult to manage the heap than it is to manage the stack. Explicit heap dynamic variables do not really have names. They are stored in memory that has been allocated and deallocated explicitly by runtime instructions that the programmer wrote. The way in which we reference them is through the use of pointers or reference variables, which hold the addresses at which these values are stored. Their primary advantage is that it provides a mechanism for dynamic storage management. This is important because there are times that we will need to do work with large arrays of data where we may not know in advance exactly how large an array we will need. Dynamic storage management allows us to make the necessary changes while the program is still running. There is, however, a downside. Heap dynamic variables can be inefficient and unreliable. For example, if you have data stored in a linked list, which is usually implemented using explicit heap dynamic variables, we have to search it linearly. The ways in which we can search an array, such as by a binary search or hashing, won't work with heap dynamic variables on a linked list. Explicit heap dynamic variables exist in many languages, including PL1, Pascal, C, C++, and Java, to name a few. And there are different ways in which we allocate them. PL1 used the allocate command to allocate storage, and the free command to deallocate it. This is similar to the use of new and delete in C++. These are all keywords in these languages, as is the new operator in Java. C handles this differently, using a collection of library functions to allocate and deallocate memory locations. Java differs from these other languages in that it will automatically free explicit heap dynamic variables when you exit the area of the program to which they belong. This is safer than requiring the programmer to do it explicitly, which can lead to memory leaks, where the memory is still allocated but is unreachable because there is not a valid pointer or reference variable holding its address. Implicit heap dynamic variables are bound to heap storage when they are assigned values. Strings and arrays in Perl, JavaScript, and PHP are allocated in this way, as are all variables in APL. This allows us to set a JavaScript variable equal to an array of integers, even if the variable was previously used only for scalar values. It also allows us to create and manipulate strings, blissfully oblivious to how memory is managed when doing this. The use of implicit heap dynamic variables gives programs in these languages an enormous amount of flexibility. And code can be written that makes truly creative use of storage. But there is a downside. It is very inefficient because everything about these variables can change. That means more time is spent dealing with allocating storage for these variables, because their storage needs can change even within one lifetime of the procedure. And this makes it a lot harder to perform type checking and to spot other runtime errors.